In this lecture, we are going to talk about normal forces and friction in detail. So we have met normal force a little bit earlier in one of the previous lectures, and we know from the basic theory of normal forces that this is a contact force which exists between any two surfaces that are physically touching. All right, this force always acts perpendicular to the surfaces in contact. And why is it called a normal force and denoted with capital N? Because mathematically, normal is just another word for perpendicular. So since the force is always perpendicular to the surfaces in contact, we term it a normal force. So there's a statement in understanding normal forces that is N, or normal force, is just as big as it needs to be. For what? Either to stop things from accelerating. For example, consider a book sitting on a desk and it is at rest. Why is it not falling through the desk and into the ground? Because of normal force that exists between the table or the desk and the book. The normal force is the opposing force which is always perpendicular to the book, exerted by the table on the book, to keep it from not accelerating through the table. Okay? Or it can also be that normal force is just as big as it needs to be to cause something to accelerate or to cause something to move. And we will see an example to examine both of these conditions so that it will be more clear then. Friction is another kind of force that we will like to study. Friction is denoted with a small f, and it is also another type of contact force. But this force exists between surfaces with the purpose of opposing the surfaces from sliding against each other. And the common idea or misconception about friction happens to be that friction is a force that opposes motion. It is not always the case, because it doesn't oppose all kinds of motion. Friction only opposes sliding motion. Sliding is the key word here. So what kind of motion does friction doesn't oppose? Well, actually when you walk on the ground, friction helps you to maintain a stable form so that you can walk without slipping or sliding on the ground. That's why it is harder to walk on ice or snow than it is to walk on concrete grounds or even dry surfaces. Okay, because drier surface means more friction and so more stability against sliding. Okay, so friction opposes sliding, not motion in general. That is very important to understand. There are two types of friction that we will study in this course. One is static friction and two is kinetic friction. What is the difference? Well, static friction is the friction that exists between two surfaces that are in physical contact, and one surface is trying to slide over the other. It is not quite doing that. It is not quite sliding as of yet. So that's why static friction is as big as it needs to be to prevent one surface from sliding on the other, but this friction is not unlimited. So if you overcome that limiting friction, that limiting static friction, then you would be able to make that surface slide over the other surface. And so the definition of static friction is not definite. It is Fs is less than or equal to mu s times n. What is mu s? Mu s is the coefficient of static friction. Coefficient of static friction depends on the surface in question. For example, a wet surface will have a smaller coefficient of friction, while a dry surface will have a higher coefficient of friction. So both mu s and mu k, they depend on the surface in question and the property of materials. Okay, and n is the normal force. So we can see that friction is related to the normal force, and we can see that this is a direct relation. So if you have a higher normal force, you would also have a higher frictional force. Now let's move on to kinetic friction. Kinetic friction is the friction denoted by F sub K. K means kinetic and here S meant static. It is much more simpler. How is this different from static friction? Kinetic friction exists between two surfaces already sliding against each other. So whenever an object starts sliding over another surface, then the friction, if present, is considered to be kinetic friction, which is Fk equals mu k times n. Again, k here means kinetic and mu k is the coefficient of kinetic friction. Okay, now let us investigate these two properties through an example. Let's say you have a box that is sitting in your bedroom and dust is collecting on it. Your mom comes in and she wants you to move this out of your room as soon as possible. Okay, but it is very big, and if you're like me, then it's probably hard for you to move. Then to move this box, you would need to exert a significant amount of force, right? Because you're like me, skinny and not as strong. So what we have here is this box sitting in your room on the ground. So this box has a mass, so let's call that our weight is equal to m times g, as we have learned so far. And since it is in contact with the ground will exert a force on the box, which we now know as the normal force, right? And see that this is the ground and the normal force is perpendicular to the touching surfaces, the surface of the box here and the ground it is sitting on, and the normal force is perpendicular to it. Then let's say you want to move it in this direction, so you want to make it accelerate in this direction. What you would do is you would want to exert a force size capital F towards the right. Okay, let's not worry about the axis at this point. This is the situation here. Okay, so to move this box, you need to apply a significant amount of force. We call that F, and these are the other forces acting on the box. When you try to move it for the first time, you'll find it hard because maybe this is too heavy, right? So your initial force was not high enough. That is what this statement really means. Fs is as big as it needs to be up to a limiting point for it to oppose sliding. So if you are to slide this box across the ground, then you have to apply a certain minimum amount of force. Before that, the box won't move. Why will it not move? Because of static friction opposing your sliding motion, opposing the fact that you want to slide this box through the ground. All right, but is this infinite? Can you never move the box? Well, no, because you can move the box if you exert a large enough force. So if the force is larger than whatever this Fs is for your ground surface, so remember Fs is equal mu times n, so friction depends on the coefficient of friction of the surface that you're trying to slide the thing across. If this surface is very rough, we say that the friction is very high. Why? Because then coefficient of friction would be very high. But if it's smooth, then friction is not as high and you would need to exert a smaller force. All right, so at any point when F becomes larger than Fs, your exerted force becomes larger than the static friction, then box starts sliding. But before that, when F is less than or equal to the static friction, box remains at rest. All right, so this is why, because of the existence of these limits, static friction is defined as a limiting condition. However, kinetic friction is not like that. Kinetic friction would exist between the box and the ground at the point when the box starts sliding. So from here on after, we have kinetic friction. Okay? So after you have exceeded or you have exerted a force larger than your static friction, you already have made the box start sliding across the floor, which means now since the box is already sliding, our friction changes to kinetic friction. Alright, so that is the basic difference between static friction and kinetic friction. Now, to understand more about normal forces and friction, let us first consider one example involving just normal forces where we are choosing to ignore any friction that might be present. Alright, so the question reads, a book of mass 1.2 kilograms, the mass of the book is given to us, is at rest on a desk. What is the normal force on the book exerted by the desk is the first part of the question. Before reading the second part, let's just carry out the first part. So by now you should be aware that the first thing you do in solving any question in physics is draw a free body diagram. So our free body diagram is, we have the book resting on a desk. First force we draw, as always, is our weight, which is the weight of the book, mass of the book times g, acceleration due to gravity, directed downwards, and the normal force that exists between the desk and the book. So the desk, if it's the desk, then desk will exert a perpendicular force on the book. All right, so also we must choose the axes that we work with. So I am choosing rightward to be positive x and upward to be positive y, the usual directions. So how would we go about finding what this normal force is? First of all, whenever you're working with forces, your go-to move is always Newton's second law. So first write down general statement for Newton's second law. F is equal to, summation of F is equal to ma. Now this is a one-dimensional motion, since the book, all the forces on the book being considered is along the y-axis. So we can choose to work with Fy, right? So summation of Fy is equal to m times ay. So what is the summation of Fy? So we sum all the forces in the y direction. What are the forces in the y direction? We have N, we have mg. So N is directed upward, so positive. Mg is directed downward, so negative. All right. So this is why we don't need to insert a negative 9.8 like we did for projectile motion, since the sign comes out organically when writing down Newton's second law equation if you have done your free body diagrams correctly. No other forces present, so equal to mass times acceleration in that direction. Now this book is at rest. All right, at rest means it is not moving, so it cannot have any acceleration, so this side becomes 0. So to solve for n, we have to add m times g to both sides of the equation. So here m times g cancels out. Here we have 0 plus mg. So normal force is actually just the weight of the book, which turns out to be n equals 1.2 times 9.8, which is n equals 11.76 newtons. So don't confuse this n with that n. This n refers to the unit of force, which is Newton, while this n refers to the normal force magnitude. All right. So here in this case, when the book is at rest, then our normal force is nothing but just the weight of the book in question. Now let's move on to the second part of the problem. The second part reads, a string is tied to the book and you pull on the string to make the book move upwards. Just before the book starts to move, you are pulling the string with a 3 Newton force. In this question, what is the normal force? Alright, again, the first thing you do, like always, is draw the free body diagram. Our free body diagram is, we choose the same axis, plus y plus x. The box is here. This is my weight, mg. The normal force still exists from the desk, but now we have a second force, which is, let's call it Fp equals 3 Newton. Fp is the pulling force that you are exerting on the string when you pull the book up. Alright, then we write down Newton's second law, and since all of these forces are in the y direction, we can just write the y equation. What are the forces? We have 3 Newtons going in the positive y direction, so positive, N going in the positive y direction, and mg going in the negative y direction. And again, just before the book starts to move, so still not moving, so again acceleration in the y direction is 0. So N becomes, solve for N, add mg to both sides first, and then subtract negative 3 from both sides, we get mg minus 3. Here we can see that the normal force is actually smaller than the weight. This is the weight by 3, right? So therefore the new normal force, that's funny, is 8.76 newtons. This illustrates that the normal force can be equal to the weight when an object is not moving in the vertical direction, it is at rest and no other vertical forces are acting on it. However, whenever another vertical force acts on it, the normal force will be different from the weight.